Good morning, everyone. I wanted to start with this quick little demonstration here. This is a pretty straightforward demonstration on how important it is to have a scale that has a lot of graduated markings. And so if we're trying to measure the length of some sort of an object, and this also is trying to help us maybe understand what we mean by significant figures. Obviously, this object that I'm trying to determine the length of here has some actual length. The question is, how well can we determine it with some sort of device or some sort of measuring tool? And so you can see if our first scale, we're using this one here, we're gonna have a hard time interpolating anything better than probably calling that maybe 14, I think that's centimeters, so about 14 centimeters would probably be as good as we can do with the top scale. And if I use the next one down, it's a little bit better where you can see this is just over 14. Oddly, from my vantage point, it doesn't look as much across 14 maybe as you guys do from the way the shadowing is working. But we could probably say this is about 14.1, 14.2. So we can pick up an extra significant figure. We can characterize the length of the object to a little bit of a greater precision with the scale that has more graduated markings. And then with even more graduated markings, we can do even better. And so if we're really careful to line this up, and if you can probably not entirely see from your vantage point, let me move this over, we can pick up another sig fig. I won't determine what the actual sig fig is here, but we can sort of see the graduated markings. Maybe if we get really good with our eyesight, we can see that the marking is between two of those dash marks. So if we're in the middle of our two dash marks, we can pick up an extra decimal place. So instead of calling it 14.2 centimeters, maybe we can determine it's 14.25 centimeters and pick up an extra digit. And we can use even, we can use digital scales, we can use other types of means of measuring the length of this object to characterize it and try to get at the understanding and the determination of that true value. So the object has some actual length that we could determine very precisely if we had the most precise instrument in the world, or if we use the actual scales available, we can determine it to maybe 2 sig figs, 3 sig figs, 4 sig figs, depending on our ability to actually just read the scale and use the scale. We can see this a little bit with graduated cylinders and the example. Let me switch over the main screen. We can see this a little bit with the way that we use graduated cylinders. Graduated cylinders are intended to have a bunch of markings so that we can very precisely determine the volume within the cylinder, so that we can determine volumes to maybe the nearest tenth of a milliliter. In the lab, you'll be using things like burettes and pipettes that get you an extra decimal place. If you want to be even more precise, we have other glassware that we can use. If you haven't used a burette, it's kind of like a graduated cylinder that's in a big tube and then has a little valve that you can use, open up and pour out from the bottom. But it's kind of like a really skinny and long graduated cylinder that lets us determine, because of the extra graduated markings, those volume readings to the nearest hundredth of a milliliter. So we can get really precise with those tools. So let's look at this question here that's asking us to determine the object, determine the density of an object, where we know the mass of the object. We determine it maybe with an analytical balance where we determine that to a bunch of decimal places. And we place this object into a graduated cylinder where our graduated cylinder was originally filled with, say, water, and we determine where the water line was filled to. Then we add our object, and it's going to displace water. It's going to move the water upward, change its volume. So our water goes from 75.5 to 124.0 milliliters in our graduated cylinder. So imagine we just have maybe like a solid piece of metal or something that we're putting into this graduated cylinder. So can we determine the volume of the object? Well, of course, volume is just the mass to charge ratio. So we obviously know the mass right off the bat, because we're told it's 49.9724 grams. And then what's the volume of the object? Well, the volume of the object is how much water it had displaced. So the water went from 75.5 without the object to 124 with the object completely submerged. So it's just that simple difference here. Now, this obviously becomes a significant figure question. So we can calculate the density. I think that's pretty straightforward. But the question would be, or the question I'll have for you guys to spend a minute or two thinking about this is, well, how many sig figs do we get here? So let's take a look at the math. Think about the sig figs for a moment or two, and then I'll wrap up and conclude, and we'll move on to our next slide. So how many sig figs would the difference of the volume have? So throw it into a calculator, we get 48.5. And that's precise, those 3 sig figs are our 3 proper sig figs. So I have 124.0, I subtract 75.5 from that, I get 48.5. I'm good to the tenths place. So I have tenths place minus tenths place. It's all about the placeholders right here. And so my result is good to the tenths place, which happens to end up with 3 total sig figs. So I'm not necessarily counting 4 sig figs minus 3 goes to 3. I'm just looking at the placeholders. I'm looking at tenths place minus tenths place is rounded to the tenths place. However many other placeholders there are on the other side of the tenths place are just however many I happen to end up with. And so if we had, if the initial volume of the water were a lot higher, then we may have had even fewer sig figs. If the initial volume were much lower, we would have had even more sig figs. So it really just depends on how many placeholders we have leading to that tenths place. So we look at our placeholders for addition, subtraction, and then multiplication, division, we count sig figs. 3 sig figs divide into 6 sig figs. We round to the lesser quantity. So we would round this, of course, to 1.03. We'll see a few more sig fig questions as we kind of go along. So we'll think about sig figs. We have a couple more slides still from chapter 1, but even when we get into chapter 2 slides, we'll see a few review problems over significant figures. Yeah. Oh, yeah. I am apparently having ADD issues this semester. So yeah, this is our density, not volume. Thank you. So density is mass over volume. I wrote volume is equal volume over, yeah, so density is mass per unit volume. Okay, so let's go over a couple things about dimensional analysis. We've already talked about dimensional analysis a little bit. I just want to make sure that we're good with trying to use dimensional analysis as itself for converting units. So often we think of using dimensional analysis for solving the problems like how many seconds are in a year, problems of that variety. But we'll see that we also use them a lot for problem solving. So we'll do an example second where we just kind of do a density type problem where we can use dimensional analysis as a means of helping us solve the problem as a math tool. And then we'll look at converting some units where we'll try to convert like weird cubic units that comes up in this chapter. So let's look at the first question here. How many grams are in 2.25 pounds? What I like to make sure that we're on the same page here is I don't expect that you memorize really almost any conversion factors between non-SI units and SI units. The only primary conversion factors that you're going to need to know how to use are like the prefixes, like centimeter to meter, millimeter to meter, micrometer to meter. Those types of conversions are what we expect that you know. These non-SI units will give you the conversion factors if you need these on exams. So the key step here is just starting with what we're looking for. We want to know how many grams are in 2.25 pounds. So that's a good starting point for using dimensional analysis. This is, as we get into more advanced problems, sometimes we forget to do this step, and sometimes we get in the middle of the dimensional analysis step and kind of forget what it is we're trying to determine. So it just helps us stay in tune with what we're trying to determine. We want the grams from the pounds. We get the kilogram to pound conversion. So 1 pound is, 2.2046 pounds are 1 kilogram. And we've talked a little bit about how we probably wouldn't want an ordinary measurement like our 2.25 pounds to be rounded based on our sig figs and our conversion factors. So we're either going to use an extra amount of sig figs on our conversion factors. We may have to look these up when needed. Or in some cases, the conversion factors are exact. It turns out this conversion factor is actually rounded. So if you wanted to look this conversion factor up, I believe it's defined to like 10 or 12 decimal places. So this is the pound to kilogram conversion is a very precise, precisely defined quantity. Here we're just using 5 sig figs. That's plenty for this problem. And then of course the kilogram to gram conversion to finally go to the unit we're looking for, 1,000 grams in a kilogram. That's perfect in terms of our sig figs, exactly 1,000 grams per kilogram. A lot of times, sometimes we get confused over when I'm using my sig figs and thinking about significant figures, I have 3 of my 2.25 pounds. I have plenty in my conversion factor, so that's not going to lead to a rounding. And then this is exact. I'm not rounding to like 1 sig fig here. There's exactly 1,000 grams in a kilogram. So I don't need to worry about the sig figs and my conversion factors here. So just doing the math real quick and then times 1,000. So I get 1,020 grams with 3 sig figs. So 3 sig figs, we end with 3 sig figs. So then can we use within a dimensional analysis sequence involving, say, a density conversion? So we have a question that says how many pounds of ethanol are present in a gallon of ethanol? So let's say you have a gallon of ethanol. We know we're given the gallon to liter conversion. We're given the density of ethanol. And so from these quantities, hopefully we can make this conversion here. So again, let's start with the number of pounds, what we're looking for. And we start with the gallon. We're told 1 gallon is 3.7854 liters. Now, we get the gram to milliliter, so I just have to know to go from 1 liter to milliliters. So 1 liter is 1,000 milliliters. So I'm doing that conversion so I can use my density conversion as a conversion factor. And so it maybe isn't obvious, like perhaps you're looking at this problem and you could be saying, well, why don't I just solve for the volume in milliliters and then plug into like D is equal to M over V. You could totally do that. There's nothing wrong with looking at density as an equation and trying to plug a density in. You can plug a volume in and solve for mass. We could totally do it that way, but we could, I think more simply in a problem, just be able to use the density this way here. We go 0.7894 grams per ml. The volume cancels. And so just by tracking the units, we know that we're going to multiply by the density. So probably the only real question would be, do we multiply by the density or do we divide by the density? But we just have to write our units out, follow them along accordingly. Now, I can tell you that as students from your end, the most likely cause of a mistake on a math problem on a test is not writing units out. Because when we do dimensional analysis, if we're not writing our units, then we're multiplying or dividing, and we're guessing at that point if we don't follow the units. So if you're really careful to put the unit you're converting in the denominator, and then our new unit in the numerator, cancel it out in the denominator, then we get towards the unit that ultimately we're going to try to determine, which isn't gram yet, but we're getting there. So we're in grams right now. We just have to get to kilograms and then to pound. So 1,000 grams per kilogram. And then that same conversion for 1 kilogram is 2.2046 pounds. So just doing the math, 3.7854 times 1,000 times 0.7894, divide by 1,000 times 2.2046. So I get 6.59 pounds. So now, to think sig figs for a minute, just to make sure we're clear on this, 3 sig figs, I have plenty of sig figs in my next conversion, exact sig figs in my next conversion. Then here I have 4 sig figs, so I'm still keeping with 3. Perfect sig figs, exactly 1,000 grams per kilograms, and then plenty of sig figs in my pound to kilogram conversion. So all multiplication, so 3 sig figs to start. Nothing's changing that. There's nothing with fewer than 3 sig figs, so I keep all 3 sig figs in my result here for 6.59. I hope I bore you with this sig figs. If I bore you, you get it, that's good. There's always a question or two on the first exam, and hopefully you find them to be very easy. The sig fig question should be easy because there's just a couple of rules, just rounding to the placeholders for addition, subtraction, rounding to the number of sig figs, the fewer ones for multiplication, division, and then sequentially applying the rules for multi-step problems. Okay, now for one last conversion type problem from chapter 1 is that the conversions involving cubic units. So we deal with cubic units a lot. You can convert area units as well, like square meters to square centimeters. We can think about how those conversions would go. And the key here is thinking that we're going to use the same conversion, like a meter is 100 centimeters, but how does that then help us convert a cubic meter into cubic centimeters? So let's think about this conversion here. How many cubic centimeters are in 1 cubic meter? Now, the conversion factor that we all know, and that is the one that is easy to know, is this one here, that we know a meter is 100 centimeters. But obviously, a meter is not a cubic meter, so my units aren't quite canceling out yet. So now let's think about a cube for a minute that's a meter by a meter by a meter. So if you imagine a cube that has those dimensions, its volume in centimeters would be 100 by 100 by 100. So if you're just picturing this cube here, and again, I'm a terrible artist, but if you're just picturing 1 meter by 1 meter by 1 meter, that's going to be equal to 100 centimeters by 100 centimeters by 100 centimeters. So if you're converting 1 meter to centimeters, that's 100 centimeters. That's 100 centimeters. And then the other meter is 100 centimeters. So all I really need to do, if I'm going to cube the meter, is I have to cube my entire conversion factor. So there's a few ways we can think about the mathematics of this. So I can think about cubing the entire fraction. And so if I cube the entire fraction, then what that would do is it's going to cube the 1, which is of course 1. It's going to cube the meter. It's going to cube the 100. It's going to cube the centimeters. So what I can do whenever I'm converting a cubic unit, like cubic meters, is I look at, well, cubic centimeters, I have to cube that conversion factor. So 100 centimeters per meter, for 1 cubic meter, it's 100 cubed centimeters cubed. So if I'm cubing this unit here, for my conversion factor, I just need to cube the centimeters in that conversion factor. So 1 meter by 1 meter by 1 meter is 100 by 100 by 100, which is 100 cubed. And so when we do this conversion here, 100 cubed is, I believe, 1 million, just to make sure. Yep, so that's 10 to the 6. Cubic centimeters. So a lot of cubic centimeters in a cubic meter, but we can carefully calculate that just using the simple ordinary conversion factor between meter and centimeter. So in other words, when we do cubic conversions, we don't have to really look anything up. You can do these conversions without any extraneous or extra conversion factors. And so now sometimes a question like this comes up where either it's just like directly converting the units of density. So this question here says convert the density of water from grams per milliliter to grams per cubic meter without looking any conversion factors up. Or we can do like another type density problem like we just did with the ethanol problem, where we give you like the ethanol density in like kilograms per cubic meter, and then you have to do the same problem. So sometimes you see this within a density question like the previous one we solved, or just a straight converting the units of a density from one unit to another. Now there's just one other conversion factor that is probably known by most of us in the room, but there's one other conversion factor that's worth knowing. And so I think this is really the one key conversion factor for this chapter, is that 1 milliliter is 1 cubic centimeter, that this is an exact conversion. And we just have to know this one. So this is probably the one conversion factor that's pretty obvious. We've probably seen it before. But this is a conversion factor we're going to need in this problem to have understood and to be able to use. That's not going to be given to us, but it's also really straightforward. And so that's how we go from milliliters into cubic centimeters, and then that's how we get into cubic meters, we'll see. So if we're looking for the number of kilograms per cubic meter, and we're starting from 1.00 grams per ml, I hope that you can see that the dimensional analysis thought is the same. What we're looking for and what we're given, and then how we're going to go from milliliters into the cubic meter is going to be through the cubic centimeter. So 1 milliliter is 1 cubic centimeter. So I'm just converting that unit. And then the cubic centimeter, as we just saw, so I have 100 centimeters in 1 meter. But in order to cube, if I'm going to cube this, I need to cube everything else in the conversion factor. So to cube the centimeter, cube the 100, cube the 1, which is just 1, of course, and then cube the meter. And then that takes us from cubic centimeters into cubic meters, and then we just need to convert grams to kilograms. So 1,000 grams per kilogram. And so this will work out to be 1,000 kilograms per cubic meter. Just to double check that. Yep. So this will be 1.00 times 10 to the 3 kilograms per cubic meter. Just to go to 3 sig figs here, where all the other sig figs in the conversions, of course, were exact. Exactly 1 milliliter per cubic centimeter, exactly 100 centimeters cubed in a meter cubed, and then exactly 1,000 grams in a kilogram. And again, I hope the sig figs are boring, just trying to hammer out as many examples as we can with those. Okay, so with that kind of completes most of the examples I wanted to cover from chapter 1. We'll see some embedded sig fig questions throughout chapter 2. So pretty much every lecture from here on out until we get into midterm 1, which is not next Tuesday, but it's a week from next Tuesday. So we're getting there, about a week and a half away. As soon as we get to that first midterm, hopefully we see a bunch more of this sig fig question, just because that's the one question that you're going to see throughout lab a bunch. You're going to see it in other topics. So we have to really get good that significant figure portion of the class. Okay, so let's head into chapter 2. So chapter 2 is on the topic of atoms, molecules, ions. If we're thinking about, how this first couple chapters goes in this class, we kind of go from basic chemistry, math introduction, chapter 1. Obviously, we want to talk about what compounds and matter are made up of, so we get into atoms, molecules, ions, chapter 2, and then we get into chemical reactions next after we get through chapter 2. So I think we make a kind of obvious starting point here in this class of the topics that we get into. So we'll talk about chapter 2, the discovery of atomic structure, and what we know about modern atomic structure. A lot of this you guys certainly know about protons, neutrons, electrons. You may forget which ones are which and where they are, but you probably remember from probably as early as 7th, 8th grade science that protons, neutrons in the nucleus, electrons surrounding the nucleus. A lot of this stuff you guys are pretty well versed in. We'll go through a review of what those are and also how we came to know some of this information here in this chapter. We'll talk about atomic weights, the periodic table. Every element has a listed number, for carbon, it's 12.011 on this periodic table. We want to know what that average atomic weight means. We'll talk about it here in this chapter. That's a way we can look at each element, how many different isotopes they have, and how we take a weighted average of all the ones that exist naturally. We'll talk about that topic in this chapter so we can know how to use a periodic table and understand its information that it's giving us. And then we'll get into understanding a little bit about a small little picture of structures of molecules and ions, but really just more looking at some different formula and trying to determine what type of compound it is. And then from that type of compound, be able to give a name to the compound. So just some basic nomenclature so we can talk about different compounds and understand some important classes of compounds. We can start to predict a few properties we'll get into later just from knowing what type of compound that we're dealing with. And so to kind of get a start to atomic theory, the thought of matter being comprised of spheres of atoms and atoms being kind of spherical in nature was being developed in the early 1800s by Dalton. And so Dalton was really just coming up with the idea that there's probably different elements and that things are comprised of different types of elements. So different substances just have different types of atoms or particles that were beginning to be called atoms around this time. Though this is without any direct observation. So this is like certainly well before scientists were taking any kind of a glimpse into the actual electronic structure nature or the actual like real, it wasn't like we could take X-ray structures at this time and get like structures of molecules. So this is all just like thought experiments leading to some of these sort of ideas. And so then atoms of the same element were thought to be identical to each other. So like if you had iron, then you had a different iron sample. And so maybe you took iron ores, heated them up, so you got just down to the pure iron. And if you remember, we were talking a little bit about in chapter 1, how in the early times, what you would do is just take a substance and try to see how many times could you break it apart. Can you break it apart into something? Well, they got to iron and they couldn't break iron down. So iron was thought to be an element. You can do the same thing, lead to something that they would call zinc, because it had a different set of properties, it had a different density, a different set of melting points and things of that nature. And so they were determining different types of metals first, because those are the really easy things to kind of cook up, heat up, and then get to a substance that would never change once they got to one of those elements. So they thought, okay, these elements would be identical to each other. So if you had a block of iron here, a block of iron here, that whatever it is that makes iron iron is identical. Well, I think we now know that most elements can exist as different isotopes, but certainly the thought of what an isotope was completely unknown to scientists in the early 1800s. An idea that could we take iron and somehow convert it into zinc? Can we convert one element into another element? Well, that seemed to be challenging. They weren't able to do this. And so pretty quickly they were able to come up with an idea that once an element is a particular element, it's staying that element, and we're not chemically changing it into some other element. So if you have carbon, you're not turning it into nitrogen by any kind of natural or chemical means. Now, we'll get into a little bit, maybe it's a 1220 topic later, you'll get into some radioactive decay processes. We'll actually see something radioactive today and how we can tell it's radioactive. But things that are radioactive are turning into other elements, but those are through natural phenomenon that we can't really control. We can't even stop those transformations from happening. So there are decay pathways where one element may be over time converting into some other element. And those are very interesting processes, but those aren't things that we're going to control by chemical means. So we're not interconverting elements. So I think that's good to know. And I think we know that already from examples we've seen in science to this point. And then compounds form when we take elements and combine them together, and then they tend to combine in whole number ratios. And so this is like where you get the idea that if you take carbon and oxygen, you can get CO, so one carbon for every one O atom, or you can get one carbon to interact with two oxygen atoms, form carbon dioxide, so that when you're forming elements together, they go in whole number ratios. So we get formulas where you have either a 1-to-1 ratio or a 1-to-2 ratio. So you get whole number ratios of elements forming when they form compounds, just meaning that compounds have some sort of formula that relates to the ratios of those elements. If you're thinking of some problems where we determine what a formula is, that's a chapter 3 topic. A really memorable problem for most students are those percent mass problems where you go from like a percent mass of a compound into a formula. We'll see how to do those problems in chapter 3. But here in chapter 2, we talk a little bit about the law of conservation of mass. So we're not, through the course of doing reactions or combining elements, we can't change the overall mass. We start with some mass, we just interconvert it to a new mass that's the same mass that we start with. So when we do a chemical reaction, we're not destroying matter, we're not creating matter, we're just simply changing the nature of the bonding between the elements. So if we start with elements on the left side of, say, a chemical reaction, we end up with the same amount of elements and mass on the right side of the reaction. And the law of multiple proportions just says that when we combine things, that's the whole number ratio. So that just says when we're forming compounds, we get, like a ratio like for CO2, 1-to-2, or 1-to-1 for carbon monoxide. Just that elements react with some sort of proportionality. Okay, so let's get into some of the theory of electronic discovery. We actually have the ability to see some of these experiments ourselves. And so J.J. Thomson, 1897, was able to discover the electron through an experiment that we can replicate here. Let me turn the lights down here. So this is kind of like a cathode ray tube. This is like the old style TVs that you guys may not have ever seen. Those big old computer monitors. And so what those would have is electric discharge that if you fire an electron at a screen, it would light the screen up. You just have different screens of different colors. You just would fire different electrons at different screens, and it would give you your color piece. And so that's basically what we have here. So we have a discharge tube that I can turn this on here, and you can see a discharge. And so what this is a flow of electrons here. And so the way J.J. Thomson determined that this is an electron, one of the ways is by taking the magnetic wand and just seeing that we can deflect that particle here by using a magnetic field. And so if that were just like a laser pointer, so imagine I was lying to you, this is really just a bunch of light. Light doesn't carry mass, so light particles aren't going to deflect. I wish I had a quick laser pointer to show, but if I had a laser pointer, I can't deflect a light beam just with a magnetic wand, but I can deflect a particle. And so what this seemed to be was the discovery of the first subatomic particle. So when you think of an atom, this is the first time they're able to say, well, we're taking something off the atom and detecting it, and so they call this particle the electron. 1897 is when this discovery is being made. And so then another discovery was, or another way to see that the particle is actually, another way to see that that particle that we're creating here is actually a particle, not just a particle of light, is you can try to move an object. And so we can shoot a stream, kind of the same stream that we're creating here, at a little pinwheel inside of this glass vessel. You probably can't quite see it yet, but there's a little disc, and if I turn this on, I should be able to spin the pinwheel. I don't know how well you guys in the back can see that, but those of you guys up front, you see something spinning. And so that's the particle hitting it and making it spin. So again, if I just took a laser pointer and fired a laser pointer at something, it's not going to make an object start to slow. There's no mass there to create that type of motion. And so this is just really showing us we have a particle that's being created by whatever is in this device giving off a particle. So the high voltage electricity that we're using from this source here is taking that particle off and then firing it across that we're seeing as that arc. Okay. And so that's the discovery of the electron. We'll get to this one here in a minute. I won't need the lights turned down, so let me turn them back up. Okay, so the idea here of what J.J. Thomson was able to determine was the mass-to-charge ratio, which isn't worth memorizing the numerical value, but the numerical discovery here was the mass-to-charge ratio by taking the magnetic field and seeing how much it bent this particle. Okay, so the next important discovery was through Millikan's oil drop experiment. And so what Millikan was able to do was he atomized an oil spray. This is just a way of taking an oil and just breaking it apart into like individual, say, carbon atoms and say oxygen atoms. So you're just atomizing the spray of an oil, and then you have all these particles that are then suspended that you can then allow to drop through a chamber here. And then they were hit with an X-ray source. The X-ray source is kind of like a high voltage source. It's a high energy source of radiation that could kick a particle off or create electrons or negative particles on those atoms. And so then what was determined is that you could have spheres with 1 or 2 or 3 or 4. So they're looking at the multiples of charge, and then we're able to deduce down to just what the charge of one of those particles would be through this experiment. So what this experiment was able to determine, the key detail here, is that it determined the mass of the electron. It was able to determine very precisely, using that mass-to-charge ratio from the previous experiment, it was then able to determine, well, what is the actual mass? What is the actual charge of the electron? And again, this isn't a number that's worth memorizing, but the idea that this is the experiment that then determined just how light the electron is, and also determined the charge of the electron in coulombs. Again, not a number worth memorizing, but it just was able to determine the actual charge on the electron through this experiment. So we got the discovery of the electron itself previously on the cathode ray tube experiment, and this oil drop experiment about 10, 12 years later was able to determine the actual mass of the electron. Now this is where you could see that the mass of the electron was very, very light. I mean, much, much, much lighter than any known element at that point. And so this is really where you're seeing that this is an incredibly small, incredibly light particle compared to the atoms it must be falling off of. And so this is giving the idea that the electron must be a very unique type of particle and just how small it is. And so then another question would be, well, where is the atom? In order to understand the next experiment, let's talk about Marie Curie's work in 1903 on radioactivity. 2 Nobel Prizes for Marie Curie for her work on studying radioactive material. And so one of the piece of work she did was she put a radioactive substance in a lead block and was able to pass the particles being given off through electric fields that then could separate into 3 key types of particles. And so kind of in a similar way, this is a more dangerous experiment. I believe she died at a young age from cancer developed from studying these radioactive pathways. But you can see 3 different types of particles being given off. One of them was the negatively charged beta ray. This is the electron. So one of the particles being given off by radioactive substances is just simply that same type of particle that J.J. Thomson was discovering. So instead of using a high voltage source to create that electron, this is just a radioactive piece of uranium. I can't remember if it was uranium or polonium that she was using. But there is just a radioactive metal that's just naturally giving off that particle. And then if you put that magnetic wand, it went up towards then the positive direction. So the idea here of determining charge is like if you know this is the plus side of your field and you got a particle traveling up towards it, then that particle must carry that negative charge. And so that's how we knew that was the beta ray. That's what was just the same type of electron given off from the cathode ray tube experiment. And then also there was a positive particle that went downward, but notice that the downward particle doesn't go down as much as the negative particle goes up. And so this is showing us that this particle here is just much more massive. So there was a more massive positive particle that later was determined to be the nucleus of helium. So later this was determined to be a helium nucleus, which isn't so important that you know that and memorize that detail either. But one of the interesting things of radioactive material, because I've mentioned before that uranium's the biggest known element that naturally occurs on Earth. All the elements that were bigger presumably were created in the Big Bang and then have over time been decaying into smaller elements. One of the key pathways is for an element, if you go 2 across uranium, so go to plutonium. Plutonium, if you imagine it losing a helium, like the particles of a helium off of it, you end up with uranium. And so one of the key radioactive decays of elements is they form a really stable helium nucleus, and that's one of the key radioactive pathways. And so that's just the more massive helium nucleus. And so this is probably about 4,000 to 6,000 times more mass than the mass of 1 electron. And so you just have a lot more of the mass being carried in that part of the atom. So naturally the next question was, or what we're gonna see is how this experiment helps us when we start to try to see, well, where is the actual mass of the atom? Is it all in the atom? So do we have the positive particles, well, we now know neutral particles too. Do we have those particles and electrons all coexisting together, or do we have the massive nucleus form where you have all those positive particles in a really small compact nucleus? So that's going to be the next question. One other detail is that you see a third particle, a gamma ray. This is actually just a high voltage form of light. So this is just really high energy electromagnetic radiation, not a particle. So the gamma ray is just basically a light particle, but of really high energy. Think of an X-ray of even higher energy. So a really high energy particle being given off by this radioactive substance. So now this plate here has a paint on it that has some uranium in it, and so you can pick that up. So this is a Geiger counter, so it picks up whenever there's particles being given off that are radioactive. And so I'm told I can, well, I don't know if I was supposed to do that. But this is just picking up those radioactive particles coming off of a piece of uranium. And then I wasn't quite sure of the point of this, but I will show it, and then maybe, again, I don't know what this, you see some color up here, so I'll have to figure out later what it's supposed to be shown there. This is the new demo. So that was supposed to be showing us something that I don't know what it's supposed to be showing us. But apparently that plate has uranium in it too. So. Okay, so radioactive substances undergo decay pathways. The key is that one is the electron, another is a helium nucleus, and a third is a high packet form of energy. We're going to use one of these particles in our next experiment. So the real reason I think we're discussing this experiment is So when we get to this experiment where Rutherford was firing the alpha particles, so the alpha particles at helium nucleus, so we're going to fire a bunch of helium atoms at a piece of gold, okay? And so what Rutherford was trying to discover, or what he was trying to study or examine is this how elements are constructed? You know, are we going to take the positive particles, what we now know as neutrons in the atom, the neutral particles, are we going to take those particles that we're going to see are much more massive? Because you can understand that if an atom's subatomic and the electron's very light and had the negative charge, then the mass must reside in the positive particle. The positive particles must carry a lot of the mass. Are we going to have that light particle and heavy particle all coexisting together? That was called the plum pudding model. That's what's kind of shown here. You could probably think that that's a pretty bad model for the atom to choose. You probably wouldn't want to have some sort of fast-moving negative particle and a slow-moving positive particle in the same basic space. So to try to study how the atom was arranging its subatomic particles, these helium nuclei, the alpha particles from Curie's work, were fired at a very thin piece of gold foil. And so now you can think of a few things. You could think if we just have a bunch of random positive particles, this is probably going to go straight through. This is kind of like almost like thinking of shooting like an X-ray at your leg. They're not going to necessarily, it's not a great example because X-rays aren't particles, but you would probably imagine if you had a really thin, like say, piece of tissue, and you fired a big particle at it, that it would go straight through. And you would probably, and what Rutherford was expecting, if this was the model here, that the particles would have all went straight through the piece of gold. That the gold would have been so thin that there really would have been nothing in the way from these particles going straight through. And what turned out was that a lot of the particles are actually scattered. So we saw a scattering of a lot of those particles. And the reason why we were seeing scattering is because the gold foil must have had a compact nucleus that had a really, really high mass compared to the helium nucleus mass. So we're firing a relatively massive particle at a thin sheet of gold. The thought would be that there's probably enough room between all these particles that that particle should go right through, but instead there were these massive, you know, in terms of how much mass the nuclei had, such that if this particle, as it's going through, hits the nucleus, it deflects off, because that nucleus has enough mass to withstand the hit for the particle to eject off and change its angle. And if we had a model like this, the particles would have all just went straight through, would have been the thought. There just would have been, the particles themselves probably would have had such a low mass that even if you hit a positive particle with that fast-moving, highly massive charge, it just still would have kept going straight forward. And so the discovery of the nucleus was made through this experiment by just finding that we were seeing scattering at wide angles due to the presence of those nuclei. And I like this quote here that Ernest Rutherford said of his experiment. He said it was quite the most incredible event that has ever happened to me in my life. It was almost as credible as if you fired a 15-inch shell at a piece of tissue paper and then the shell came back and hit you. Because that was the thought, was we're firing such a high-moving and fast particle that's going to go straight through. And the fact that some came back at wide angles was then showing that we had a nuclear structure, or a structure of that atom that hadn't yet been thought of. And so Rutherford, the next slide will show a picture of it, was able to then, through his experiment, let me summarize this one first. So Rutherford's gold foil, or the alpha scattering particles, so we're scattering the alpha particles, those helium nuclei, and the gold foil experiment allowed the discovery of the nuclear model and the nuclear nature of matter just due to that wide angle scattering. And that can only be explained by the presence of massive nuclei. Now the other, just to give a quick summary of kind of like what should you take away from this topic. Thomson discovered the electron, late 1800s. I like to set the stage just for like when are things being discovered about nuclei. We'll get into the periodic table a little bit more in terms of its fundamental discovery, I think in chapter 7. But we'll see at this time, like the periodic table was kind of like proposed, but there are a lot of holes in it at this point. So it's not like we knew a whole lot about the periodic table just yet. And so end of the 1800s, early 1900s, where we're really starting to discover the subatomic nature of matter. So just know the cathode ray tube allowed the discovery of the electron. It determined the mass to charge ratio of the electron, so that Millikan can then discover later the actual mass and charge of the electron through the oil drop experiment. So Millikan, 1909, discovering the mass and charge of the electron. Curie helped us understand radioactive decay pathways, helped us get a particle that we can then fire at gold in our Rutherford alpha scattering experiment. And then finally, the actual discovery of the proton as a particle, 1919, we don't talk about how it was discovered, but I think it's worth noting that the proton itself, the positive particle, 1919, and then I don't think this name has even ever come up on anything, but Chadwick is the name who discovered the neutron, 1932. I just like bringing up the year of the neutron being discovered. That's a neutral particle in the nucleus. I mean, this is after my grandma was born. So I mean, it just seems so recent in our history that it's been only in the relative short history that we've known about, you know, all the elements on the periodic table. Only within the last few years have we really filled in. I said before, like we've really filled in the full periodic table. We should update ours on our wall to reflect that over the discovery from like particle physics of those really heavy nuclei through their work. But we've really now, like just recently, really understood the full periodic table, electronic structure, and really have a good understanding when we talk about matter of what it is that we're talking about. So it's really just over the last 100 years or so that we've been able to put this all together. Okay, so let's take a look at this nuclear model. So again, you've probably seen this before, but Rutherford's postulate was that you have this nucleus that has the mass. So that's where we're going to have our protons and neutrons. So our protons and neutrons are going to reside in the nucleus, and then our electrons, they're going to be doing things outside the nucleus we'll talk more about in chapter 6. Chapter 6 gets into things like s orbitals, p orbitals, d orbitals, if you've seen these before. If you haven't seen them, we'll talk about that in chapter 6. If you've seen it, hopefully give you a good review of that in chapter 6. So if you remember determining things like 1s2, 2s2, 2p2, that comes up in chapter 6. And so the nature of the electron is very, very complicated. So we're not really trying to show that complication here, but just that the electrons are probably doing something outside the nucleus. Electrons are fast. So you probably want the electrons, if they're going to be spinning or doing something around the nucleus, you probably want them spinning around that charge. You don't want them bumping into that charge. This works out pretty well. So our negative particles outside the nucleus, that charge is holding them into place, giving them the reason why they would want it to be around that nucleus in the first place. So most of the atom is actually space if you think about it. So most of the mass is being resided by a very small compact nucleus, and then the electrons, almost no mass at all. So atoms are pretty much empty space, but that empty space is useful because that's where the electrons are spinning. So they need that space so that they can exist within the space between atoms. So imagine we had two atoms next to each other. They're going to be pretty far apart, so their electrons can have their space. And if you could picture two atoms next to each other, their electrons repel each other. So you can't just like stack nuclei right on top of each other. Okay, so then let's get into kind of like a relative mass kind of like picture of like what's the mass of the proton, what's the mass of the neutron, what's the mass of the electron. This atomic mass unit scale is one that we'll define it in terms of an actual conversion factor into grams later, but just for now, just know that there's a conversion factor for AMU to grams. So like AMU, we can convert this to grams just with a simple conversion factor. So whenever you're looking at the mass in AMU, the conversion factor is actually recognizable. So it turns out that 1 gram contains 6.022, and we could write that more precisely. I'll just go ... to imply more precisely. We can know that number and then times 10 to the 23 AMU. And so I'm sure you guys know that number. What number is that? Avogadro's number, of course. And so there's an Avogadro's number of AMU in a gram. So I think it's useful just to kind of see the idea that when we talk a lot in chapter 2 about AMU, because AMU is a really convenient scale when we're talking about the mass of just one single atom. Whenever I talk about a mass of a collection of atoms, that gets into like a mole scale. We talk about mole in chapter 3. So we'll see in chapter 3 Avogadro's number come up, how it converts like the mole into like the quantity. So you might remember that. That might be a little fuzzy. We'll get into that in chapter 3. But for now, I just want you to think that the gram to AMU just is a very simple conversion factor, and one that you actually probably recognize the number. But when we look at the mass of the proton, it's about an AMU, about 1 atomic mass unit, 1.0073. Again, not worth memorizing that number. The neutron's about the same. It's a little bit different, but it's in that same ballpark. And then the electron, just look how much smaller it is compared to the mass of the proton and the neutron. So a lot less mass residing on the electron compared to the positive particles and the neutral particle in the atom. Another thing, when we start getting into like talking about the isotopes of a given atom, like you might know that carbon most commonly exists as carbon-12. It also exists not as commonly, but about 1% of carbon's carbon-13. We'll get into a little bit later. I think there's a slide in a few moments that gets into exact percentages, but we're about 99% carbon-12, about 1% carbon-13, and a very, very small trace of carbon-14. But when we start thinking of like, okay, how can I make sense of a symbol versus the periodic table? Like how do these particles match up? Like if I look at carbon, it's element number 6. You may not be able to see it with the screen there, but on the periodic table, carbon's the 6th element. That's shown here if we want to write in this number here. This is what we call our atomic number. The atomic number defines the number of protons in the nucleus of the atom. The positive particles in an atom, like hydrogen's element 1 has 1 proton, helium's 2 has 2 protons in its nucleus. The number of positive particles in the nucleus is really what's going to determine a lot of the properties of that atom. And then this number here is our mass number. And this is where a majority of the mass exists in our nucleus. So that's the number of protons plus the number of neutrons. So if you sum up the protons, you sum up the neutrons, because that's where the mass lies. So the mass number are the particles that actually give the atom its total mass or most of its mass. The electrons give such a small amount of mass, we don't add the electrons up into the mass number. And then our charge is kind of indicated out here. For the most part for now, we'll be talking about charge neutral atoms. So our charge would be shown here as being neutral. So this is our charge. And the charge of the proton is exactly the same as the electron, just opposite in sign. So it's helpful to know that electrons and protons have the same charge. So if I know 6 protons for carbon, it has to have 6 electrons. So in order to get a neutral charge, I'm going to have 6 electrons to balance out my 6 protons for like the carbon-12 atom. And we'll do a bunch of examples of this, but I just wanted to set the stage for a couple of things here. One, we could look at the periodic table. We can get from the periodic table the number of protons in the nucleus. We can get the atomic number. To determine the mass number, you can't just like necessarily look at the periodic table and determine what the mass number is. You have to know a little bit of information. So we can't always just predict the mass number of the most abundant isotope. That's actually a tricky question. A lot of times you can look these up. If you go to like isotopes of like oxygen or nitrogen, if you were curious, you can see a listing online or in a CRC index. You can look up what the most abundant isotopes are, but you're not going to predict these percentages here off of anything. If you know them, you know them, but there's no way to predict these just from something on the periodic table. But one thing I wanted to mention is that you might think that for carbon-12, what I would want to do to determine its mass is take 6 times the neutron mass, 6 times the proton mass, plus 6 electrons, right? That's not actually how you come up with the mass of an atom. In fact, there's an interesting concept much later in chapter 23, that if you add up the mass of the subatomic particles, those are a resting mass. The particles aren't resting when they're in the atom, they're moving. The electrons are spinning, they're moving a lot. And so if you compare the difference of mass you would sum up versus the actual mass of the atom, that's the nuclear stability. So there's a lot of nuclear stability energy. So the actual mass of carbon-12, you just have to know this or look it up. It turns out, and we'll see this a little bit later why this is relevant, that it's 12 AMU exactly. Because it's actually going to be the element that we use to like anchor down what an AMU even is. So we use carbon-12 to determine and just say, well, that's 12 AMU exactly. That's going to be important for how we determine the AMU scale. And so carbon's 12 AMU. Carbon-13 is not exactly 13, it's 13 plus a fraction, so you actually get a real mass for carbon-13 where it's not defined by some scale. But we'll talk about what the mass of carbon-13 is later, but it's about an AMU higher. But for now, what I wanted to talk about, electrons, protons, same charge but opposite sign. This helps us count up protons versus electrons. And then we can get symbols, we can get mass numbers, we can think about things called isotopes. Carbon-12 and 13 are isotopes of each other. They differ in the neutral particle. So think about how the difference between carbon-13 versus carbon-12 is that here we have 7 neutrons. The protons don't change because that would change the nature of the atom. So carbon-13 compared to carbon-12, the difference is 1 extra neutron. So having an extra neutral particle in the nucleus for carbon. I'm going to allude to this slide because we'll start here next time just counting up and determining protons, neutrons, electrons for an atom like chlorine-35 and some other atoms. So we'll pick up from this slide next time. Thank you guys, have a great day.